Today I will start by discussing tangent planes to simple surfaces, or coordinate charts. And to begin that, I first want to remind you of some of the notation that we're going to use throughout this class. So x is going to denote a coordinate chart. It goes from an open set in the plane to R3. And P is going to be a point that we're focused on the surface. And it's always the image of some point in the plane, A, B. Now recall the definition of a coordinate chart. The function needs to be one-to-one and smooth. Also, the partial with respect to u1 and the partial with respect to u2, evaluate those at P, you get a vector. Their cross product should not be 0. And this should be true at all points, but in particular the point we're focused on. Now we're gonna follow the book, and we're going to use just x1 for that partial with respect to u1 and x2 for the partial with respect to u2. Often I'm not going to put that we're evaluating it at A, B, but for the most part you should just remember there's this sort of one point P that we're focused on, and we're evaluating these at that point. Now the tangent plane at P, the definition of it is that it is the plane that passes through this point P, which has normal vector that's given by the cross product of x1 and x2. Okay, and like I've said, I'll often just write x1 cross x2 for the normal vector without writing the evaluation at A, B. Okay, so that's our object we're going to focus on, that tangent plane at P. Now let's make sure that we understand how these calculations are going to go. So I'm going to do an example of a tangent plane for a particular surface. Okay, so let's consider the surface that is defined by x of u1, u2 is u1, u2, u1 times u2. Find the tangent plane at these 2 points. And I'm going to say that you should pause it at this point if you would like to work that out on your own. Now let's write down the partial derivatives of x with respect to u1 and u2. With respect to u1, of course, we starts off with the first component being 1, second component 0. The third component, since it's u1 times u2, partial with respect to u1 is just u2. Something similar happens with the partial with respect to u2. You get 0, 1, u1. And then when we take the cross product, you should remember that anytime we have a graph parameterization, which this one is, this is for the function f of xy equals x times y, you can write out the cross product x1, x2 in terms of partials of that function f. So negative partial with respect to u1, negative partial with respect to u2, 1. That's always your cross product. At the point P, we have u1 equal to 1 and u2 equal to 0. So our cross product gives us 0, negative 1, 1. And then when we put that into the equation for a plane, we get negative y plus z equals 0. To compute the tangent plane at Q, we notice that u1 should be 1 and u2 should be negative 1. So when we put those into that formula for the cross product x1 cross x2, we get 1, negative 1, 1. So that's our normal vector, and the plane passes through the point 1, negative 1, and so we see we get this equation for that tangent plane, and that simplifies to x minus y plus z equals 1. We'd like to make sure that the calculations that we make, the tangent plane and also the normal vector, are independent of which chart we use. So the first thing to do there is to use a unit normal vector. Okay, we take our normal vector and just divide by its length. And we'll call that little n. Okay. Now, the vectors x1, x2, n, these vectors make a basis of R3 at each point on the surface, much like the Frenet basis for a curve. Okay, but it's very important to note that this is not necessarily an orthonormal basis. Okay, even if you make all of them have length 1, you can't guarantee that x1 and x2 are orthogonal to each other. Okay. But at the very least, if we do some things with that unit normal vector, by forcing it to have length 1, that unit normal vector up to a sign will be the same regardless of which chart we use. Okay. The next thing that we want to worry about is we really want to make sure that this tangent plane that we've defined actually does not depend on the chart that we use. Okay, so we have to ask the question, if we have charts X and chart Y, both giving us the same simple surface, do they end up defining the same tangent plane, right? Do those charts give us the same tangent plane by our construction? Okay, so the way that we're going to try to answer this is we're going to take two charts and we're going to check that the span of x1, x2 and the span of y1, y2 are actually the same. Okay. So how are we going to determine whether the span of x1 and x2 is the same as the span of y1, y2? We need to discuss how the chart y is related to the chart x. Okay, and this involves thinking about the fact that the chart y is going to the same spot as the chart x. So chart y, we're going to suppose that it has a domain, some open set V in the plane. The coordinates for that are going to be v1, v2. Okay, and let's assume that the image of that chart is this little coordinate patch around the point P, and that it's the same as the image of X. Okay, so we have this sort of a schematic. I'm going to call C, D the point that Y takes to P. Okay, notice that C, D in the v1, v2 plane, Y takes it to P, and then if we follow that with X inverse, then we're taken over to the point A, B. Okay, so what we end up getting is a function g given by X inverse composed with Y, which goes from the open set V to the open set U. So the output of g is in the U1, U2 plane, coming from the V1, V2 plane. Okay, and this function transitions from the domain of Y to the domain of U. Now, what's important for us is that g is going to be a differentiable function. Okay, with the kinds of surfaces we're going to work with, it'll actually be a coordinate transformation. And this gives us a relationship between the two charts. Y is equal to X composed with G. Now, calculating partial derivatives, we're going to end up with the Jacobians of these maps. Since y is x composed with g, the chain rule tells us that the derivative of y is the derivative of x times the derivative of g, all evaluated at the right place. Now, these derivatives in this case are the matrices of partial derivatives. Okay, so J of x is a 3x2 matrix. J of g is a 2 by 2 matrix because G has 2 coordinate outputs and X has 3 coordinate outputs, right? So on the right side there of that equation, we've got a 3 by 2 matrix times a 2 by 2 matrix. When we evaluate them at the right place, for Y and G evaluating at C comma D, X at A comma B, then we get matrices with numerical entries, right, instead of just functions in the entries. So this is an honest matrix product on the right, and so this equation is going to really help us understand why the coordinate charts don't change the tangent plane. So the next step is to notice that so J of X, its columns, right, since we've evaluated, those are exactly x1 and x2, the vectors whose span is equal to the tangent plane at P for the chart X. J of G, when we evaluate at its point, its columns are just vectors that have 2 coordinates. Those are scalar coordinates once we've evaluated. They're just numerical entries. Okay, so what we want to think about is J of X times a single column of J of G. Okay, what we get when we do that is we get a linear combination of the columns of J of X, right? Those scalars multiply by the 2 columns and add those up, and that gives us our linear combination of x1 and x2. Now remember that G goes from the v1, v2 plane to the u1, u2 plane. So it's telling us how those coordinates transform. So its partial derivatives are the partials of u1 with respect to v1 and v2, and the partials of u2 with respect to v1 and v2. That's how we get the entries in that Jacobian matrix. So the partials of the u coordinates with respect to the v coordinates, those evaluated at the right spot, those will be the scalars that come up in our linear combination. More precisely, y1, the first column of the Jacobian of y, is this linear combination of x1 and x2. Notice that those partials of u1 or 2 with respect to v1, those are scalars when evaluated. As a consequence, y1 and y2 are linear combinations of x1 and x2. So a near linear combination of them is also, and the span of y1 comma y2 is a subspace of the span of x1, x2. But they have the same dimension since y1 and y2 are independent. Y, after all, was a coordinate chart. And so these spans are, in fact, the same. So this tells us that the tangent space is independent of coordinate chart.